We are going to introduce the speaker of the next talk, Dr. Yuandong Tian from Facebook Artificial Intelligence Research.
Good afternoon, everyone. I'm so glad that there are still a lot of people left after AlphaGo's talk. My name is Yuandong Tian. I'm from Facebook AI Research. I'm a research scientist there. DarkForest is an open source computer Go engine that developed majored by me and also my colleagues that also use deep learning to achieve a strong engine. But I mean, definitely DarkForest is not as strong as AlphaGo for sure. But it's open source and anyone can download the code and use it and study how the Go engine works. So today I'm going to talk about the computer side of the Go, how a computer should design, and how we should design a computer Go system so that it becomes strong. So people all know the game of Go, so I will basically skip these slides. And one sentence is a minute to learn and lifetime to master. So this is the gist of the game. So I hope everyone will enjoy the game of Go. So the interesting about the Go is it has two different aspects in the game. So people all know the rules. I will not repeat it. The game is actually very, very interesting because we all have a 19 by 19 board that you can place a stone at any location of the intersection. But if you ask professional players how you play so strong, they will never say, oh, I emulate all the possible solutions and find the best move. So people also have the feeling saying, yeah, this is a good move, that is a bad move, and I choose to play this good move because part is because it is my feeling, and the other part is because I have some computation showing that that move is actually good. So this is make the computer Go very interesting because it unites pattern matching with search. And also it combines reasoning and logic and intuition together. So how you model that actually could give you a different level of computer Go program. So computer Go has been developed for like 50 years. So at the beginning, people start to use rule-based system with alpha-beta pruning, but that actually give you a very low level computer Go program. So what do I mean by rule-based? I think not everyone is majoring in computer science here. I mean, if anyone who have no computer science background and ask him to write a computer Go program, what would he do? He will say, yeah, I'm a strong Go player. Oh, I know all the rules. And let me write down all the rules one by one. And then basically I will write them into the computer program so that the computer can actually understand this rule and follow this rule in specific situations. But if you do that, it's not a good idea actually, because there are so many rules and so many intuitions from a Go master that you never enumerate manually. So that's the reason why you have a very low level Go program if you follow that paradigm. Then what you get if you actually change the search algorithm. So traditionally people use alpha-beta pruning. Alpha-beta pruning is basically saying, yes, let's just emulate all the possible moves from the current situation and use some clever pruning technique to find, okay, he is very, very bad because the opponent has a counter move. So once we find that counter move, we do not need to find all the other counter moves for that move. So we can say that entire move is bad. Okay, get rid of it. So this can actually reduce the number of search, but to some extent, but not really can resolve the problem. And in 2006, people have developed Monte Carlo tree search, and that's actually a better way for the game of Go. So Monte Carlo tree search, if you think intuitively, it's nothing but just a stochastic way of doing alpha-beta pruning. So instead of enumerating all possible moves and find the best moves, they find 4 candidates that are very, very good. And then they basically find which path is the best move by randomly sample the game search space and use that to expand your tree. So this gives you a very good program that is achieving the top amateur level, but not anymore. So after that, people will say, yeah, in order to improve Monte Carlo tree search, we still need to go back to the rule-based system to actually make things better. But this actually you see this vicious circle there, and people will not be able to make things a little bit better. And after that, since 2014, we have seen a new trend of how we should model how the computer play the game. So we use deep convolution network. Once we use deep convolution network, it's actually give you a new way to model the data so that a lot of internal connections or internal relationships can be modeled automatically from the data rather than by yourself or by a human labor. And this actually give you a much better, stronger Go engine. So this go all the way from 60 to beyond a 9-down professional player, which is the AlphaGo level right now. Before I actually introduce the reason, the architecture of DarkForest, I first talk about this overview. This project is proposed by myself, and then I, with my together with one of my intern last year, work on it. It starts at last May, and then we spent like half a year on this and achieving strong amateur level. We actually talked with Aja yesterday and talk about we used like 80 to 90 GPUs to train this model. And I would ask like Aja, how many GPUs do you have? Aja say, this is confidential, I cannot say. But then I ask about then like could I say like we are using like 1% of the GPU that you are using? I just say maybe less than 1%. So that's probably the resource difference between DarkForest and AlphaGo. But I'm still very proud that although with this huge difference in resources, we are still able to make some progress. And we actually are the first one who put our deep convolutional network-based approach, Go engine, onto the KGS, so that all people can enjoy the game versus the new generation of the Go engine. And finally, for the name of the Go engine, the name is after the Sweet Body Problem Volume 2, the DarkForest, because I'm a big fan of that novel. So the strengths of DarkForest. So if we purely use the deep convolution network, it's KGS 3-down level. If you put DCNN with the traditional Monte Carlo tree search, is KGS 5-down level, but it's quite it varies a lot because sometimes it's actually very, very strong. Sometimes when it makes mistakes, it will become pretty weak. So that's still a problem that we need to solve in the following in the future. So it won like 3rd place on KGS January tournaments, and actually it won like the 2nd place in UEC computational Go competition. Recently we also beat 6-down professional player with 2 handicap, but that's I think it's pretty we're pretty lucky to get this achievement. So history of DarkForest is like this. So first, as I mentioned, in last year, 2015 May, we start our data collection. We find this could be interesting direction, and we could work on it. And we actually see the pure DCNN working and put them onto KGS, which is last August. And then we get Monte Carlo tree search working on November 2015. I think by that time, I think AlphaGo has already finished their Nature paper and send them to for review. This is quite so basically like we are actually chasing in this half a year. Then we have our paper accepted in February, but before that we have seen AlphaGo's news. And then we made a bunch of improvement after that. So it is now open source with a lot of popularity. So we open source with a BSD license. So with this license basically means that you can use that code for any reason. There's like no particular restrictions. You can use it for commercial software. You can use it for any software you want and keep it secret, not public. The entire code has very little dependencies, and it should be easy to install and run it. So it also come up with a pre-trained DCNN model, KGS 3D. So I think with this model, you can easily achieve a 3-down KGS level. and it runs very fast. So it runs like a fraction of seconds. So I think in the next competition, I think all the bots will be at least KGS3D using if they use that model. So we also open source our learning-based default policy, and we are training our new viral network, but we haven't published, we haven't like open source that yet. And also the training code is not open source yet. It will be released very soon. So then I will talk about how Go engine works. I think all people here are professional, are very good players in Go, but not necessarily very good programmers for Go engine. So people are very familiar with how human play Go, but not necessarily know that how computer play Go. So it's very different from human. So the first sentence I want you to remember is computer is not the god. Even with a super computer, it's not possible to search entire space. So there has to be some trade-off between efficiency and strength. So if we start with a current game situation. So what computer can do from the current game situation is the computer can expand the search tree from the current level. So the search tree here, this is the root node, is the current situation. And then from this root node, what you can do is to play the next move. There are several ways in playing next move, and you will have several sequent played moves. And then you can basically expand the next node again to expand your tree. So you can do that. So this is extensive search stage. But as I mentioned that it's not possible to go all the way to the end of the game for all branches, not possible. So after a while, after you reach some step, for example, if you reach here, then at some point you need to say, yeah, let's stop and evaluate the current game situation to the end of the game. So this evaluation step will directly give you the consequence of the game. So for example, for the node on the top, it says black wings. From the node on the bottom, it says white wings. So you have this restricted search paradigm. So you can have an engine that is strong enough, but at the same time will not take too much computational power. So then in the second stage, you will think how we should design these two parts. So for the extensive search part, you have to think about how to expand a node. It's called tree policy. So you start here. There will be like maybe hundreds of possibilities for you to place a move. But there will be a few moves that are particularly interesting. And also it coincides with human's intuition. Human never think about all the possible moves in the game. He will think, yeah, maybe here is a break point, and you need to play it here. And there you have a critical, like narcotic point you need to point. So because you have all this, it depends on like how you expand a node, you also determine what a tree look like. And the second problem is which node to expand. So we use Monte Carlo tree search. We actually know that which node we can expand. There are so many states here, but associated with each state, there will be win rates estimate. So Monte Carlo tree search almost always find the nodes that has the highest win rates, plus on exploration score. So on the second part, the evaluation part, there are also like a few different ways to do that. What you can do are basically two things. One is you can use default policy to simulate the node to the end of the game and see the consequence. So what do I mean by simulate? So we start from this node. We know that we are not going to expand the node in a tree fashion, but what we can do is to simulate the moves that each player plays until the end of the game. So in this fashion, you can find the solution, find the end situation of the game without expanding the game. And the other way is you can use a value function. For example, you train a model that directly takes that situation as the input and ask a model to give you a number. The number could say, yeah, maybe black wings, maybe white wings. So there are two ways of doing this. So here I will talk about a little bit in detail about what is Monte Carlo tree search. medical tree search is you aggregate win rates and you can search towards the good ones. So in medical tree search, it's actually quite easy to understand. So you start from an existing tree, and every time when you do a selection, you select the nodes with high win rates to explore. For example, the high win rates here, and then you do this iteratively until you reach a leaf. So once you reach a leaf, you expand the leaf according to a tree policy. Once you expand the leaf, and then you evaluate that leaf using default policy or using like value function, and then maybe that value function say, yeah, maybe black wings. Then you broad propagate your black wing information all the way back to your root. So by this way, you will accumulate win rates on every node of the tree. And next time, when you want to further explore the tree, you will be biased towards the high win rate node. So the good thing about the medical tree search is that it's not using equal effort on all branches of the game. It is using only the effort on all the most promising branches. So you will see that in some branch it's pretty shallow, but some other branches you will see a very deep dive into that branch because the computer thinks that branch is very promising and need to like further developing. So maybe after a while, the computer finds that yeah, there's a counter move in that branch that will kill all your previous effort. Then the win rates of the entire branch will soon become very, very low, and the computer will try to explore other branches. So that's how the engine works. So the one thing why Go is hard is because the policy and value function is very hard to estimate. So if you compare with chess, Go is actually a game that requires more intuition. For chess, a good evaluation function is you can basically count how many pieces you have. If you are behind by a knight or by a rook, then it's likely that you are behind and you probably will lose the game. But for Go, I think everyone just knows that if you lose like maybe 10 stones, doesn't matter at all. You can gain like a large territory on the other side of the game. So simply counting is not counting like how many stones you have captured is not the right way to evaluate a game. So and also for Go, 1 stone difference will completely change the game. And also even the order of the game, who play first, will change the game in a current situation. So this is traditionally extremely hard to model. So what people do before deep learning is to use heuristic approach. As I have mentioned, people who have Go knowledge try to dump their mind into a piece of paper and then just ask computer to follow the instructions and to find, oh, yes, maybe this is bad, that is good. So it's very slow and hard to tune because you will have like maybe thousands of rules and they may be conflicting. Some people say this, some people say that, and you need to find the weights between the two, saying that that rule is actually overriding that rule, but this is going to be extremely slow process, and finally it needs very strong Go experience on this. So how to solve this problem? The answer for now is deep learning. So we can use like end-to-end training to train the model, given lots of data. So instead of asking the people to write down rules, we can ask computer to find the rules from the data. So I think this is like the next way, much better way in modeling this kind of complicated structure of the problem. So it has very less human intervention and minimum Go knowledge required. Like for me, I'm really a bad Go player, but still we can develop quite a good engine. So and finally, I have seen that it has amazing performance. So the idea of a neural network attempt is not really a new idea because people have seen that a long time ago. So in 1990s, you will see people try using small size network and shallow networks, but they are not successful because it seems like the performance is not as good as if you hand tune or the parameters if you put like more rules into the system. So people will say, yeah, it's slow and it's hard to tune and it's not as good as existing systems. Forget about it. But once deep learning comes and people start to use models that has many layers, you will see things changes a little bit. So first we see papers from University of Edinburgh that is published from ICML 2015 that achieves 4K to 5K level with a deep neural network. So this is quite good compared to that stage, because people traditionally think if you just use evaluation, just say, oh, I just play by intuition, it's very hard to achieve 4K to 5K level by intuition. People say, yeah, you need to search over the situations to make it better. But they actually show that without search, they can still get 4K to 5K level. And then we see paper from DeepMind that they used 12-layer CNN, and they also beat Apache with 11% win rates. So it's not, this number is not great, but still I see like a substantial, very good trend following that line. So we start to work on this direction. And that's the reason we have work on that. That's the reason why we have DarkForest. And as we all see that in Nature 2016, in this January, we see DeepMind has achieved their feat by having AlphaGo there and finally beating Licedo by 4-1. So for the overview of the architecture, I will talk about the detail about like how we train DCNN and testing it, and how we implement medical tree search, and also finally what is the performance for learning-based default policy. So for DCNN in DarkForest, as I mentioned, that tree policy, which is how the computer engine is like predicting the next move, is very important. So in DCNN, what we are doing right now is we have a 12 layers network that takes the current board as the situation, and then we extract 25 feature planes from the current board. The feature planes are very, very easy to extract. For example, where are the black stones, where are the white stones, and how many liberties for a group of black stone or white stone, etc. You just put them into in the input of network and ask the network to learn what will be the next, not only the next move, but also the next 3 moves from the current situation. So we train it on a 170K KJ dataset or 80K GG Gold dataset. We achieve pretty high win rate with high accuracy. So this is not a win rate. Accuracy means that how many times how many times that the engine can predict the right move compared to the professional or very strong amateur players. So once we train the model, we put that model onto KGS, or immediately after a while, people see it goes to 3 down level, and it plays extremely fast. So that's the DCNN policy. So that's also the main contribution of that paper. So in the previous work before that paper, people try to predict next 1 move, but we find that next 3 moves is better. So you will see, if you see the figure, that next 3 moves actually give you a better win rates over Apache compared to next 1 move in the same, given the same number of epoch. So if you compare that with other approaches, at that time you will see DarkForest is stronger in terms of win rates. But I think AlphaGo is here. AlphaGo probably is even higher in that number. I think it's 80-ish, 80-ish, I think. Yeah, if you win against Apache. I think that's their network plus self-play, plus enhancement using a policy gradient. So for medical tree search, we have already mentioned that how medical tree search work. So here is the implementation details. We use a multi-threaded version of medical tree search. So by multi-thread, I basically mean that for modern computers, we all have like multiple CPUs in the machine, and each CPU can try to run different like simulations simultaneously. So what you can do is, instead of like ask one computer, one CPU to run 1 thread at a time and then go back, you can ask like multiple CPUs to run multiple threads simultaneously, and this actually give you a much faster simulation rate. So So we use like synchronized evaluation. So what do I mean is there's two separate programs. So for Monte Carlo tree search and for deep convolution network. So we have a client server architecture. So Monte Carlo tree search will say, yeah, here's a node I need to evaluate. I will send a request. And then I will wait until deep convolution network send the move back. And then you continue the search. So the communication is easy. We use Unix pipe. I think AlphaGo, they use a synchronized version. So by synchronized version, what I mean is Monte Carlo tree search say, yeah, here's a node I need to evaluate. Send it to DCNN server. But at the same time, Monte Carlo tree search does not stop. It will say, yeah, okay, I have a faster version of evaluating my current situation, which is really bad, but it's faster. And we use that to evaluate the current situation first, and then keep the Monte Carlo tree search running until the server from GPU giving you the right win rate, the right move, and then update that node. So that is, I think that's probably more efficient, but it's also more complicated to implement. So we have actually two versions. December version has 100% synchronized, and top 3-5 move from DCNN. So this sentence basically means that we just rank our move from DCNN, and then we basically pick top 3 or top 5 moves as the tree policy in the Monte Carlo tree search, and use that to search. And also we add some noise to win rates to separate the threads, but which actually is not a good idea. We actually change it. And finally, we use Apache default policy. So basically, Apache is an open source software from open source community. So there's a default policy there. We basically move it to our system. And in the March version, we actually make some changes, and we get rid of the Apache's default policy by writing by our own version of it. And then we also have various changes in the Monte Carlo framework. It's actually better. So and finally, the board evaluation. So people may wonder that in KGS, how computer could know which part of the stone are dead, which part of the stone are not dead. So it's actually very easy. What you can do is you can play your default policy 100 times. There will be possibilities that stones are dead if they have low probability of survival. So the good thing about default policy is every time it actually runs through a different paths to the end of the game. So you will see sometimes that part of the stone are dead, sometimes that part of stone are good. So if you sum all the probability together, you will see some stone are very likely to be dead, and they will be regarded as dead stone. So for default policy, there are 3 default policies in our system. So one is like there's simple, which contains only rules. There's one that can come from Apache, and finally we implement our own default policy, use rules plus learning-based approach. So if you put these two things together, you will see that it's actually even higher, better than if you just use pure DCNN approach. So for the learning-based default policy, this is actually, the idea is borrowed from AlphaGo after AlphaGo published their paper. So for current DarkForest, we have a default policy that will run 6 microseconds per move with 30% accuracy. I think in AlphaGo's Nature paper, they say they have a 24.2% accuracy default policy, but actually Ajay say that it's actually 30%. Right. So so I think this is approximately the same. But I think if you put them down to the system, there's still a gap between DarkForest default policy and AlphaGo's in the figure. So so there's still like a lot of corner cases that need to be fixed by DarkForest. So here is a figure borrowed from DeepMind. So what does that figure does is it's basically like you have like lots of professional games. You run these professional games up to a certain level of move. For example, after like 15 moves, then you apply your default policy to check whether which will be the win rates, which side will win. So ideally, the best default policy should give you the curve like this. So after maybe 20 moves, 30 moves, the default policy should say, yeah, black wins or white wins. no doubt. But because it's imperfect, so you will see a gradually decreasing curve. So the faster it decreases, the better the system performance. So here is the DeepMind's AlphaGo's very fast reward policy, and DarkForest is here. So I think there's some curves there. So there's still a gap between the two. So I'm not sure how AlphaGo overcome this. Zen and Keystone, they are also actually reply that they have spent actually 5 to 10 years in rules. Basically, they check what's wrong with the game. In many situations, the computer Go engine will say, yeah, I have 80% win rates. But all the humans say, yeah, this is really a losing situation. So the reason is for this discrepancy is because the computer wrongly judged some part of the game, right? So because of that, so the computer made a wrong judgment. So in order to solve that, you have to go through and the default policy and to see that in the simulation which part goes wrong. So once you find which part goes wrong, you can put a patch there to correct that special case. But there are so many special cases, and I mean they actually, the author of Zen and Keystone actually spent like 5 to 10 years on this. So so that's actually one of the gap here. So there's no good way to learn automatically. This is from Zen's author, but I don't know. I mean, I think definitely there will be interesting ideas to learn to solve this problem. I think Aja mentioned that it could be done by pure learning, but I see that is there any? But they refuse to say anything about the details. So I think, but over time, I think people will discover that, and so that the engine that is rather than AlphaGo will be much better. So, and finally is the part of viral network. That part we haven't put that to the system, but it turns out that, I mean, from AlphaGo's presentation, it seems that viral network is actually critical for AlphaGo to achieve a super professional level. So, I mean, the idea of a viral network is very simple. So you have one board, and then you have a neural network, then magically combine these things together and give you a win rate. So I think this is also lots of intuitions from professional players. Where the first time they see the game, they do not really play it out. They already know that who is winning. So this is basically the key for the engine to become even stronger. And also this is a key for the current engine to overcome the problem that I have mentioned, that you need to deal with all the corner cases. So if the viral network is strong enough, you don't need to deal with all the corner cases, but just the viral network will give you the number, and you can just move according to that number. So if you check AlphaGo's paper, you will see that with the policy network, without the viral network, actually there is a big difference in the performance. So if you use viral network plus your original rollouts or original default policy, so this is the default policy. So this is basically a different name for the same entity. You will see it's almost like a 500 euro, which is about 2 stone for AlphaGo. So I suspect that maybe at that time, without default policy, without the viral network, you probably cannot beat Fan Hui. I don't know, just guess. So that's basically the importance of it. So we have made some progress, saying that there's viral networks that can be trained from data, and it also achieves like 0.15 error, but there's still some problem with the training. I think the data are not enough to train a model that has better performance than existing rollout. But we are still trying to do some experiment on that. So finally, I will summarize by do some like very short comparison with AlphaGo. So for sure, their system is definitely much stronger, and their policy is the policy network is from their base network from 2015 ICR, and also they use their play to actually achieve a stronger network. And they have high quality playout roll policy. So it should be like 30% here. And they have 2 microseconds per move, but we have 6. And finally, the viral network is trained many more data than us. I think that's the apparently that's the difference here. And finally, people will say maybe AI is solved, but no, it's not. It's just starting. There's still a lot of things we need to think about. So first, like we don't really need to solve like we haven't solved reasoning yet. So I think for now, if you go through the entire presentation, you will see that computer tend to solve like a Go problem using a combination of intuitions and brute force search. So, but as we all know that when we are doing reasoning, it's not really brute force search. So when people play Go, people actually learn a lot of concept. And where are all these concepts coming from? You don't see any trace from the intersection from the architecture of computer Go engine. So how this goes from? So that's one of the things that we still need to ponder on. And second is we do not know how deep learning works yet. You put them data in, and then after several days, it gives you a magic classifier or magic regressor that give you win rates, give you next moves. Seems all natural, seems like human, but no one really knows what's going on here. So this is really disturbing, because maybe in the future people start to use the system for life critical task, and in some way it malfunctioned. So and we cannot trace down the root. So this is actually extremely important, and we are still working hard on that direction. And then finally, we do not know how to train unsupervisedly. We all need the humans Go records to start to have a good policy network, and then we can start self-play, start all the magic and things come from there. But without any data, it's very hard to do that fully unsupervisedly, which basically means there's no intuition just by AlphaGo play itself. Could we train very strong engines that can be as strong or even stronger than human being? It's not clear. So hopefully people from DeepMind could give us very good news. So that's my presentation. So if there's any questions, let me know.
Okay. So we can take a few questions.
The speed is slower than the Monte Carlo search. To me, I mean, the training model is already there. Why will it be slower than the search?
Yeah, so it's not slow if you think about like a human time. It is if you go through the deep network, it typically takes milliseconds. Milliseconds means like 10 to the minus 3. But if you run like a Monte Carlo tree search and each rollout, so for example, each playouts will take like a microsecond, which is on the order of 10 to the minus 6. So this is a difference in like 100 or 1,000 times difference. That is the difference. So, but from human's perspective, everything is very fast. But if you want to run lots of simulations in 1 second, that becomes critical, and you need to have different architectures to deal with it.
Is there any caching between board positions, or do you start over with your search on every new board position?
I think in tree search, what you can actually see here is there is like cache, because the entire tree is actually stored in the memory. So every time you go through the tree and start a new tree search, you start from here. This is the existing tree search. You start from here. All these nodes are stored, as long as well as their next moves. So you don't need to request the policy network to get all the good moves again.
So you mentioned that you originally put noise into your training iterations and discovered it was better not to inject noise during the training iterations. Is that because you're not having a problem of overfitting and local maxima and stuff?
Oh, I see. That's an open problem in in the deep network community. That entire thing is a non-convex function, and what we are currently optimizing on is basically we use gradient descent basically say, yeah, here's locally I see, yeah, this is the direction that I can go down. Let's just go down. But maybe there's a valley here, and out of the entire mountain, there's another deeper valley that we never see, right? So for now, people just say, yeah, let's just follow the local terrain to the end or to the valley. But that magically works very well. So that's really the open problem for deep learning community. So we are still work hard to solve this.
Do you have any special use of the clock where some moves will get more time to search and others will be done quickly, or is it just sort of a flat policy on time?
Okay, I think because there are different type of time management in Go engine. One management is saying, yeah, let's just fix the time that we are going to use. I believe this is probably also what AlphaGo is doing. So we have 1 minute maybe, and then use that 1 minute just to search the entire tree. And when the 1 minute hits, then there will be a thread saying, yeah, let's stop it. And once you stop it, you take a snapshot of the top few moves, and you find which move is the best, and you just play that move. Is this answering your question? Yes. Okay. Then probably need to ask RGRs. Maybe they have a different. It's already done. It's already there. I think the entire engine is basically DCNN mixed with the Monte Carlo tree search. Yeah, this is exactly what it's doing right now. So here, every time you expand a node, you actually request the server, the GPU DCNN server, to give you the best move.
So basically, the computer Go is strong enough, especially like AlphaGo. So instead of like learning the 60 or 70 on KGS, shall we just remove these human goals and just try to start training with like AlphaGo self-playing moves? Would that be another direction?
I think this definitely could be a right direction. But one thing is, I mean, DeepMind saying, yeah, it's very precious, so they never release the code. They never release all the data. So, I mean, if we can have like a 100 million AlphaGo self-play data set, then I think all the engine will become stronger. But I mean, I think this is because the resources are precious, right? So it's very hard to find them. So for now, I think people use like top professional players or maybe top amateur players game to train the model, because one essential part of the model to be trained is we need lots of data. You cannot have 5 games between AlphaGo and Licedo to train the network. It's not feasible in the current technology. Maybe in the future it's good.
When you're training the value network, you're assuming a fixed COMI of like 7.5, or
fixed what? Fixed framing?
Fixed COMI.
Yes.
And so, if you wanted to play a game with a different COMI, you would have to completely retrain.
I think so. So I think for the current stage, because the rate that you win or lose, it will totally depend on COMI, right? So if you change your COMI, then you have to change everything from scratch. But not from the policy network can be reused, but the value network you need to train them from scratch.
From a mathematical point of view, is there some kind of theory about the convergence of the training of your? How do you know it's going to converge?
I think there are some papers, some theoretical papers that can be used for showing that it's convergence. I mean, it converges with like a probability of 1. There's one paper that I can actually can show it. I mean, you can basically show that because the only thing that stops convergence is going to a saddle point. when you go to settle point, then it's going to be very hard to find which direction you will go. Locally, you will see it's flat. Okay, I am just stay here. But actually, if you go that way, there's like a very, very slow slope that can go down. But the computer didn't see it, so you get stuck here. But there's a paper showing that it's very, very unlikely to happen. So in most of cases, you will go all the way to a local minimum. So basically a local valley that seems to be good if you see locally, but I'm not sure that, I mean, maybe 1 miles away, there's an even deeper valley there. So that's basically the current situation.
We are going to take 2 more questions. Is that okay?
So we have tried that, but seems like not working quite well. So
Dynamic Comey, right?
dynamic homing, yes. Oh, I think the previous question was about if you use value network, do we need to train the model? The answer is yes, because the value network need to give you the win rates given the current situation. So this actually involves Comey computation. But if you just use value network, use like policy network with Monte Carlo tracer, you don't need to retrain the model if you change your Comey. 2 more.
2 more questions.
Yes. I think this is a very good idea. But we have tried also a recurrent neural network which can mimic your search. But it seems like the performance is not as good. So, but this, I still think this could be a very interesting direction to explore. Last question. Okay. Sorry, so I probably give too much chance in this side, that side.
Hello. As I'm an architect, so I'm very interested in whether we can train the value network system to notice what is beauty and what is ugly, and then instead of architect a human being, and it can design a building like in the future. Is it possible?
I think it's definitely possible. For an art application, people have seen Prisma. I think people may have used Prisma before, that can turn a real picture or image into an artistic drawing, right? So this is not possible in the past, but now it's made possible after if you wait maybe a few seconds. I think in the future, definitely you can use deep neural network to train a model that distinguishes between good and ugly. So I think this is actually easier than we thought about. So at the beginning, people were saying, yeah, this is something that is a mystery because we cannot tell the computer what specific is ugly and what specific is good. So we basically tell it from our perception, our sense. But it seems like right now the sense can be modeled by a deep neural network better. So I think this could be a very promising direction.
Thank you, Dr. Tian. Thank you. I have a logistic announcement. So after 4 o'clock, 4:15-ish,